Let's get started on the cryptography we use today, what you're going to be using in the organization where you work. Let's look at a high level on the two common types of encryption, and then later we'll dive more in depth on both of them. For asymmetric encryption, each person has a private and a public key, as well as it doesn't need a pre-shared key. Those are the good parts. The not so good parts is it's much slower than symmetric encryption, and it is weaker per bit as far as the encryption, which then would be the pros of the symmetric. It's much faster and stronger per bit. On the con side, it needs a pre-shared key, and all the encryption through history has been symmetric encryption. For the Spartan Cytel, we agreed on the size of the stick. On the Caesar cipher, we agreed on how many spots to move it back on the alphabet, and so on. We had a secret that only you and I knew, and because we knew that secret, we could encrypt and decrypt the message. Symmetric encryption on top of needing the pre-shared key, and this is one of the formulas I would know for the exam. N times n minus 1 divided by 2. If you look over here on the right, you can see how many keys we need for how many people. So if it's just 2 users, and we use a symmetric key, we just need 1. We need that pre-shared key, the secret we agreed upon. But if we have 5 users, and everybody needs to communicate with each other, we now need 20 keys. The asymmetric keys are pretty easy to calculate. You just times 2, whatever amount of users you have. So 100 users, 200 keys. 10,000 users, 20,000 keys. But on the symmetric side, you can see if we start moving into the hundreds or thousands of users, it becomes completely unmanageable. And also a weakness of symmetric encryption is, how do we share our pre-shared key? That gets shared securely. And we do that with hybrid encryption. We use asymmetric encryption to share the key. One of the benefits of asymmetric encryption is that we can still be secure over an unsecure medium. Once both parties have the session key or the shared key, then we switch to symmetric encryption. Much faster, much stronger, and we use that for the data transfer. And to ensure we're safe, the asymmetric encryption may send another session key every so often. Although over time could have compromised this, it wouldn't matter, because we're now using a new key. Some aggressive systems might send it every couple of seconds, where others do it every couple of minutes, or after a certain amount of packets. For the exam, obviously know the difference, but also know the formula for the symmetric encryption, how many keys we need per user. Just sit down, do 5-10 examples, and if you do a cheat sheet at the beginning of your certification, I would write that one down. One of the most common forms of encryption used in the early days of the internet is DES, or Data Encryption Standard. It could also be called single DES. For the exam, I ought to know that the standard is DES, but the algorithm is actually DEA, or Data Encryption Algorithm. So if you get a question on either of those, that's what they're asking about. Single DES, or DES itself, is no longer considered secure. Many different attack vectors have been publicized, showing ways where you can easily break the encryption. DES is a symmetric form of encryption. It uses a 64-bit block cipher, 56-bit key, and 16 rounds of encryption. It uses the Faisal cipher. We'll cover that later. And while single DES is not really used anymore, there are versions of it that still are. When people realized that DES was compromised, a competition was put out to improve on DES or come up with alternatives. What was done is similar to what the Germans did with the Enigma machine. When they knew it was compromised, they didn't just scrap it, they just added another rotor. And the solution here was to encrypt with DES 3 times, hence the name triple DES or 3 DES. And doing triple DES can be done in 3 different key modes. K1, which is the only one that's still considered secure, is using 3 different encryption keys. We encrypt it once with 1 key, then we encrypt it again with another key, and then we encrypt it again with a 3rd key, running it through the Faisal cipher, and again with the same 16 rounds of encryption. That effectively produces 112-bit key strength. K2, or key mode 2, uses 2 different keys. You encrypt with key 1, then you encrypt that with key 2, and then you encrypt again with key 1. It's not secure, and it produces a key strength about 80 bits. Key mode 3 is using the same key 3 times. It really does nothing. When you use the same key over and over, you're really just encrypting, decrypting, and then re-encrypting. You're back to square one. All things being even, the K1 or key mode 1 is considered to be secure until 2030, and is still commonly used. When they were looking for alternatives to DES, IDEA was designed. The International Data Encryption Algorithm is of course also symmetric. It's a 128-bit key, 64-bit block size, and it is considered safe today. It's not widely used because A, it's patented, which means you need to pay to use it, and it's slower than AES. AES is the most commonly used symmetric encryption. You may also hear it referred to as Rheindal. Many different encryption algorithms were entered into the AES competition, and the Rheindal algorithm was the winner. It then changed name to Advanced Encryption Standard. And it's the most used symmetric encryption for two reasons. It's not patented, meaning it's free to use. There are much stronger encryptions, much faster encryptions out there, but they're patented, so they're not widely used. And of the open source symmetric encryptions, it's one of the faster ones and the more secure. AES uses a 4x4 matrix for the bytes, and we're going to go through at a high level how AES works and the individual steps of the encryption. So in the initial round, we have the add round key. Each byte is combined with a block of the round key using XOR. Over here on the right, you can see 16 bytes, A0.0, A0.1, A0.2, A0.3, and so on. And if we look at the A2.2, it's then XORed with a key, or K2.2, which turns it into B2.2. And depending on the key length, the encryption will then go through the rounds here multiple times. In the subbyte step, we use a nonlinear substitution where each byte is replaced with another using a lookup table. We'll then do a shift row. If you look at the graphics here on the right, the A0 row is untouched. The A1 row, every byte is moved one step to the left. In the A2 row, every byte is moved 2 steps to the left. And the A3 row, every byte is moved 3 steps to the left. So for the shift row, if you look at the A3 line, it started out with a 3.0 to 3.1, 3.2, 3.3, and we ended up with A3.3, A3.0, A3.1, and A3.2. And then the final of the rounds are the mixed columns, for where we combine the 4 bytes of each column, use it to XOR, and then we start on the next round. And the final round, we do a subbytes and a shift row, but we don't do a mixed columns. And then at the end, we add the round key. As I mentioned before, the size of the key determines how many times we go through the rounds to get the ciphertext we want. We go through 10 rounds if it's a 128-bit key, 12 rounds if it's 192, and 14 rounds if it's a 256-bit key. For AES, other than the obvious, it's symmetric, it's open source, it's secure, I would also know how the initial round, the actual rounds, and the final round works, what each of them does, as well as how many rounds it goes through for the different key lengths. Let's look at some of the other symmetric encryptions you need to know for the exam. Blowfish is another symmetric encryption that's in the public domain. It uses the Feistel cipher. It's a block cipher using 64-bit blocks, and the key lengths are between 32 and 448 bits. It has known vulnerabilities, it's no longer considered secure, and the guy who developed it suggests we use Twofish instead. Twofish is similar, public domain, using Feistel, symmetric, but it uses 128-bit blocks instead, and 128, 192, or 256-bit keys. It is still considered secure. I've told you that many of these encryption forms built on the Feistel cipher, so let's take a look at what that actually is. You know that a byte is made out of 8 bits. It splits that byte up into 2 halves, left and right. It then goes through several rounds. Whatever's on the right side never changes. Whatever's on the left side changes every time. I think it's important to understand how a Feistel cipher works, but beyond what I teach you here, you should need for the exam. For this Feistel cipher, I've only used 3 rounds. Normally they have many more. And I don't expect you to be able to do this on the exam, but you need to understand in depth how it works, how the subkeys work, and how we use XOR. If we look at the byte we start with, 011, 0100. The first half gets split over to the left side, the second half to the right. And then we have subkeys. You can see the 3 subkeys we used over on the right. Key 1 is 1100, key 2 is 0011, and key 3 is 1011. So for the first round, we take our 1, or the back half of our byte, which was 0100, and XOR it with key 1, 1100. That's the first calculation in the top box. And remember, in XORing, if the 2 values you're XORing are the same, it's a 0. If they're different, it's a 1. So if we do the first bit, 0 and 1, that's a 1. The next bit, 1, 1, that's a 0. The next bit, 0, 0, that's a 0. The last bit, 0, 0, that's also a 0. So our 1 and the subkey XORed value is 1000. We then use that to XOR with the left side. The first half of our byte was 0111. We XOR that with 1000, and just like we did in the middle, if the 2 XOR values are the same, it's a 0. If they're different, it's a 1. In this case, all of them are different, so our XORed value is 1111. At this point, the left and the right side changes, so the 0100 gets moved from the right to the left, and the 1111 gets moved to the right. We'll then use the 111 and key 2, 0011, we XOR that, we get 1100, which is then XORed with the L2 value, 0100, the XORed value is 10006. Then we do another switch. The left and right side changes again, so the value we just XORed, 1000, gets XORed again with a third key. I think you get the idea by now. And then in the final step, we combine the left and the right. So using those 3 keys, 3 rounds of Feistel, our cipher byte now reads 10001100. And as mentioned, in real life, it's much more complex, but you need to understand how it works, how it swaps around, how it XORs, and then once we send to the recipient, they would have our sub keys, they will reverse the order, as well as all the other steps we did in the encryption, and that's how they decrypt our message. When I did my studying, it helped me sit down and do a couple examples like this, just to make sure I actually understood how a Feistel cipher worked, and that I could calculate it out. I don't think it's really needed for the exam, but for me it helped writing it down, visualizing it. I think writing things down improves your memory. Below here you can see all the algorithms that use the Feistel cipher or Feistel algorithm. Some you may recognize, some you may not, but just understand it is very widely used in cryptography and encryption today, and it most likely will be, at least until we move to quantum computing. Let's round out symmetric encryption with the RC encryption. RC4 is commonly used to web WPA, SSL, or TLS. The first 2 are obviously wireless, and the last 2 secure socket layer and transport layer security, used for web browsing. It uses a pseudo-random key stream, and it is no longer considered secure. For the exam, know that it's symmetric, a stream cipher, and you can use a variable key length between 40 bits and 2048. RC5 is a symmetric block cipher, and it can either use 32, 64, or 128-bit blocks, and key length from 0 to 2040 bits. It uses the Feistel cipher. It's still considered secure if we use high enough blocks and key lengths. RC6 was another finalist for the AES competition, but obviously it didn't win. It's based off RC5, but it was changed to meet the AES requirements, and it uses the Feistel cipher. It only uses 128-bit blocks and 128, 192, or 256-bit key lengths. It is still considered secure. It is also not very widely used. That's the last of the symmetric encryptions we're going to cover. There are many other types in use today, but these are the most common ones and the ones you need for the certification.